Today we are going to start Unit 3, and we're going to start Unit 3 talking about systems of equations. And to kick this off, we do have quite a few key terms that we need to familiarize ourselves with. So a system of equations is anytime we have a set of two or more equations, but they have to use the same variables. So they could both use x and y, they could both use a and b. We'll even look at some problems that use three variables, but they have to use the exact same variables. Solution for a system of equations is any set of values, an ordered pair for example, that makes all of the equations in the system true. So just like when we solve an equation and we get x equals 5, if we substitute 5 back in and it makes it true, that means it was a solution. Similarly, now we're going to look at, we have to find both x and y, or x, y, and z. An independent system, there are three different types of systems, but an independent system is going to be a system with only one solution, and it's an ordered pair where the lines cross. So if we look at this, it would be like if I did this. I've got my first line in this blue, and I've got my second line in the red, and the solution is this point. For example, it would be 1, 2. A dependent system is a system with infinitely many solutions. And what that means is that they're the same line. So if I graph this blue line, a dependent system would mean that when I graph the second equation, it is identical. It is exactly the same. Infinitely many solutions because it means that any point I pick along here is going to make both of the equations true, no matter where on the line it is. System is an inconsistent system, and this is a system with no solution. In other words, the lines are parallel. They're never going to cross, which, if we're thinking about it as a solution is where the lines cross, then it makes sense that this would be no solution, because parallel lines never cross, so they never are going to have an ordered pair in common. So these are the three different types of linear systems. We're going to look at two different things with this now. The first thing we're going to do is to classify systems without graphing. We're going to classify them as being independent, dependent, or inconsistent. So to do this, the best way is to find the slope and find the y-intercepts. And we'll look at y. So this one, I already know that this is my slope, and this is my y-intercept because it's in slope-intercept form. But this other one here, I need to change the form. So if I start with x plus y equals 3, I need to get y by itself. I'm going to subtract x to both sides. Now I have a slope of -1 and a y-intercept of 3. Here's kind of our rules. If they have the same slope, or actually let me start with different slopes, that'll be a little bit better. If they have different slopes, that means that they are going to cross at some point. It's going to look like this, and it's going to be an independent case. So if they have different slopes, right away, it doesn't even matter what the y-intercepts are. You can say that they are independent. But if they have the same slope, we see here, this line right here has to have the same slope as the blue line because it's changing at the same rate. Parallel lines, we know they have the same slope. So if there is the same slope, then you have to go to kind of a second check. You have to look at the y-intercept. If the y-intercept is the same, they are going to be dependent. They're going to be the infinitely many solutions. And if the y-intercepts are different, then it's going to be inconsistent, and it's going to be the parallel. This is a really helpful little flow chart here, so take a second, make sure you get that copied down, but that's going to be really helpful as we go through this. So again, the slopes here were different, so since they have different slopes, that means they're independent. All right, so for this one, I've got a slope of -2 and a y-intercept of -1. If I find the slope and y-intercept of that second line, I get y equals negative 2x plus 3. I just subtracted this 2x to both sides. And this is going to be my slope, and this is my y-intercept. So when I look at my flowchart, I want to say, do they have the same or different slopes? They have the same slope, right? Because I have a slope of negative 2 here and a slope of negative 2. Now, since they have the same slope, I'm going to say, okay, are the y-intercepts the same or different? Since they are different, it's going to be inconsistent. If I were to graph these lines, they would be parallel, they would never cross. So I would say that this system is inconsistent. If I graph this one, or solve this one, I'm going to have 3y equals negative x plus 9. Divide everything by 3. And we've got y equals negative 1/3 x plus 3. So that's for the first one. For the second one, I'm going to get negative 6y equals 2x minus 18. Divide by negative 6 on everything. I get y equals negative 1/3 x plus 3. So are our slopes the same or different? Are our y-intercepts the same or different? And then what does that mean? Since my slopes are both negative 1/3 and they both have a y-intercept of 3, that means that when I graph these, I'm going to get the same line. So these are going to be dependent. So that's how we can classify a system without graphing. But we're also going to graph them and see what happens. So we're going to solve the system by graphing. And remember, solving the system means finding where do they cross, what is the ordered pair that they cross, or what's the special scenario for them. It could be a no solution, or it could be infinitely many solutions. So for x plus y equals negative 1, it's in standard form. I'm going to find the x and y intercepts. So this would give me y equals negative 1, x equals negative 1. That's pretty easy. I can do that. Put my 2 points on there and then connect the dots. Oops, that is not perfect, but there is grace. X minus y equals 3. So I get x, when I plug in x equals 0 and y equals 0, when I plug in x equals 0, I get negative y equals 3, which gives me y equals negative 3. When I plug in x equals 0, I just get x equals 3. So I'm going to graph those 2 points. And now I need to find the solution. So where do they cross? Oops. It's not perfect, but I'm going to estimate that they cross at about 1, negative 2. And this would be my solution. Do you see what one of the downsides of solving by graphing is? Notice that if I get rid of that dot, it's not actually like they're crossing perfectly at that point. If I solve it algebraically, in other words, without graphing, they should cross at that point. But because I didn't draw my line perfectly, it doesn't look like they cross at that point. It looks like it could be like 1.1, negative 1.9. So graphing doesn't really allow us to do much estimate or like exact guesswork or exact work. It allows us to do a lot of guesswork and estimating, but it depends upon how accurate we are in our grading or in our graphing, excuse me. All right, let's look at another one. All right, some more standard form. We needed to practice this. So we've got Let's do this. For my x-intercept and y-intercept, I'm going to get negative y equals negative 1 and x equals negative 1. So this would be y equals 1 and x equals negative 1. Connect my dots. Again, trying to be as accurate as possible. It's just, I'm doing this by hand. It's not going to be perfect. All right. For our next one, we've got 2x plus 2y equals 10. So x equals 0, y equals 0, 2y equals 10, 2x equals 10, and both y and x are going to equal 5. All right, so when I look at where do they cross, it looks like they cross right about here. So that's going to be the point 2, 3, and that would be my solution. Maybe some of you are breathing a sigh of relief because we have something that's not in standard form. I can identify on this one that this is my slope and this is my y-intercept. So I'm going to start by graphing my y-intercept of 3 and then a slope of 1/2, up 1 over 2, up 1 over 2, over 2, etc. And then connect my dots. Next, for the second one, I have, so for this second one, we have a slope of negative 1/4, and we have a y-intercept of negative 3. So now I'm going to do my slope of negative 1/4. I'm going to go down 1 and over 4, and I can do that a couple of times. But I can also go the opposite way. And when I graph these, I'm going to see where do they cross. And it looks like they cross all the way over here at the point -8, -1. And so this would be my answer. So graphing is a really great way to kind of start talking about systems of equations because we can visualize what's happening. We see that a solution is where they cross, but graphing is the least reliable way to solve a system of equations because it relies on us being 100% accurate in our drawing, in our graphing, and so it's just not the most reliable. We are going to practice with it, but I do want to, and so I'm glad to start with this this method of solving, but we are going to look at some, sorry, I can't think of the word. We are going to start with some other methods of solving systems of equations that will be algebraic. We're going to look at substitution and elimination, and they're just more reliable because they don't rely on us graphing. So if you have any questions, if that last little bit where I couldn't think of the word confused you, let me know, and I would be happy to clarify anything for you.